Good morning, class. Today we're going to learn about Le Chatelier's principle. And what this principle guides us here is it guides us in the process of equilibrium. And you'll notice here that I have my seesaw on this title page. And that's because we're going to see that whatever you do to one side of the reaction, you're going to affect the other side. So let's get down to it. When we're talking about Le Chatelier's principle in equilibrium, we have to know first what the principle is. And the principle states that any reaction in a closed system, when stressed, has the ability to correct itself. Now, if we use an analogy, closed system means the test tube has to be sealed, or the beaker has to be sealed, or the flask has to be sealed. And we know in the laboratory environment, that can cause a dangerous system. So it's something that we don't really work with a lot in the laboratory at the high school level, but it's an important concept. Another analogy that I like to use is with cooking, because chemistry is like cooking. Le Chatelier's principle is if you have a pot of boiling water on the stove with a lid on top, if you walk away, nothing bad is going to happen. The water is going to boil, it's going to evaporate, it's going to turn to steam, hit the top of the lid, condense, turn back to water, and fall back down. Notice closed system, what goes up comes back down. If I did that same exact experiment at home with a pot of water boiling and I leave it alone with no lid, the water is going to evaporate, the water turns to steam and leaves the pot, and the pot's going to burn. So the concept of Le Chatelier's principle has to be in a closed system. And when a reaction's in a closed system, you're going to have a balance being maintained, which is called equilibrium. When it comes to equilibrium, we can tell a reaction is at this important point by examining the reaction arrows. Now, in questions, most of the time, the arrow is going to look like this. One arrow pointing in one direction, one in the opposite right below it, and notice they're equal in length for equilibrium. However, depending on the fonts that are used for different questions, you might get the arrow side by side. So one is pointing this way and one is pointing this way. You might get them where it's kind of like a little broken arrow on top and bottom. So double arrow means equilibrium. And what takes place is in a reaction equilibrium, two big things are going to occur and one's going to have no effect. The two big things are the rates of the reactions are equal. Remember, kinetics and equilibrium go together. Kinetics focused on the rates. So if the rates are equal, that means, number two, the concentrations on both sides are going to be constant. So that means they're going to be used up and put back in at a constant rate, again, like a seesaw, back and forth, back and forth, back and forth. And when we get down to it, a question that always shows up on the regions for these is the catalyst. Remember, a catalyst speeds up the reaction in both directions by lowering the activation energy and providing a new pathway. But if I speed up the reaction, I'm speeding up both directions, so nothing's going to happen. It cancels out. All right. So at equilibrium, we're going to see these three things take place. Now, how do we assess it? What is this thing that we're talking about with this thing called stress? Well, stressors of a reaction, if you think about it, could be concentration or heat. And concentration and heat go together because when I'm adding or taking away, they act the same way. So concentration or heat. When we add concentration or heat, the reaction always shifts opposite. And notice what I highlighted in red. Easier to remember, add shifts opposite. That's going to be a rule that we use to determine how a reaction is going to shift at the stressing point, and then it goes back to equilibrium. When we remove something, the reaction shifts to the same side. So add, shift opposite, remove, shift same. Now again, we want to make sure we understand what's taking place in the reaction to apply the appropriate shift, because the shift determines everything else in the problem, as you will see in a few minutes. Add, shift opposite, remove, shift the same. So let's take a look. Here I have a reaction, and notice I see my double arrow, and I know I have energy here. Now, energy has to be in the problem, or a kilojoules, if they're going to ask you the heat type of question. So I have here a synthesis reaction, good thing to review, where I'm making a bond and energy is released because it's a bond formation is exothermic. So the new concept, if we increase A, now notice it says just A, not A, B, C. So I'm shifting, or I'm adding something on the left, add opposite. It's going to shift to the opposite side. So when I add A, it's going to go to the opposite, which means the forward arrow is being favored. Now, in these questions, we have to know when the shift is going to occur and what it does to everything else. So notice, because the reaction is shifting forward, I'm getting more of this side. That's A, B, C together, plus energy is going to increase. So one part of this process is, do I know what the reaction is going to do when it shifts, or how it's going to shift? And then the second thing you need to do is, well, if it shifts in that direction, what's the result to the reaction? And we're going to do that a lot as we move through. Now take a look at B. It says, if we take out B, I'm removing B. So I'm taking out this thing. Well, we saw the rule was, if I remove, it shifts to the same side. So where is this single B? It's on the left. So if I take out B, it's going to shift to the same side, which means the backwards arrow is going to be favored. It's going to go this way. So that means this side has to go down. Notice the seesaw comparison. If I change one side, the other side gets affected. Okay? Third example for concentration and heat is if we add A, B, C. Now notice A, B, C is over here on the right. So yep, you're thinking correctly. I'm going to shift opposite, which means I'm going to go backwards. And therefore, all of these things are going to go up. And because of the seesaw, this side has to go down, and it does. The last piece here says if we increase heat. So you have to remember that heat is energy, or kilojoules, or joules, whatever they're going to use in a problem. So I treat it just like concentration. That's why we did it together. If I add heat, energy is heat, and it happens to be on the right side. So I'm going to shift opposite, favor the backwards arrow, and A, B, and C separately are going to increase, but the right side does not. So when one side goes up, the other side goes down. Okay, very important. When the other side goes down, the other side goes up. Again, the seesaw. So that's how concentration and energy work. But there's other stressors. The next stress that we're talking about is pressure. Now, again, review. Pressure only affects gases. And because we're talking about pressure of gases, what determines how the reaction is going to shift is by adding up the number of moles, or, as we learned, looking at the coefficients of the reactants and products on both sides. If there's more than one reactant or product, I have to add them together if they're gases, and that's how I determine which way the reaction is going to shift. And this one also does make a lot of sense when we analyze it. Now, when we're talking about pressure, they can ask this question in two ways. They can say, I can change the pressure or the volume, because remember, they're linked together. If I increase pressure, right? Think about it. If I had a box this big and I increase the pressure, I'm squeezing the box together so the volume gets smaller. Okay, just like we learned in Boyle's law. So if you think about it, if I start off this big and all of a sudden I increase the pressure, my box gets smaller. So if I increase the pressure, the reaction's going to shift to the smaller side. Why? If the reaction vessel is getting smaller, fewer things can fit in order to react. So I can take a decent sized box. Normally, if this was my reaction, it's going to go at a certain rate. But if I change the pressure on the box and squeeze it into something smaller, well, then obviously not the same number of moles of atoms can fit. Therefore, I go to the smaller side to alleviate the stress. And the great thing about this is what happens to one side does the opposite for the other. So if I decrease the pressure, the reaction shifts to the bigger side, right? Makes sense. If I have a box this big, right, this big, and then I decrease the pressure, the box gets bigger and bigger and bigger and bigger and bigger. Well, if my box gets bigger, I can hold more reactants and products. So I'm going to shift to the bigger side. So this one, you have to be careful because only gases affect this concept. So if something in a reaction is not a gas, you leave it out. You don't count it. You only count the reactants and products that are in the gaseous phase. All right. So let's take a look at the example. Here I have H2 plus I2 gives you HI and energy. And it makes sense. Making a bond, releasing energy, it's at equilibrium. So the first thing I want to do here is, because I'm talking about pressure, is I want to add up the sides. So remember, the mole is the coefficient. So on this side, there's 1 mole of H2 and 1 mole of I2. So 1 plus 1 is 2. On this side of the reaction, my products, I have 1 HI. So there's 2 moles on the left and 1 on the right. We do not count energy. So if I increase the pressure, remember, we're going to the smaller side. So in this reaction, the smaller side is HI, which happens to be on the right side. So I'm shifting forward to the right. And then once I know the shift, I know what's going to happen. If I'm going more forward, I'm making more HI energy. So this side is going to go up, but this side is going to go down. Again, once we know what shift is going to occur, we can predict the changes that are going to occur as well. If I decrease the pressure, I have to go to the bigger side, right? Because again, as the box gets bigger, I can fit more and more in. So if I decrease the pressure, I'm going to the bigger side, which happens to be the 2 side, because 2 is bigger than 1. And therefore, I am shifting backwards. Okay. And the H2 plus I2 gas are going to go up, but the right side is going to go down. And yes, I know I spelled favored wrong, but everyone makes mistakes. Now, if you're having issues with what's increasing and decreasing, okay, I always ask my students, if you know which way it's going to shift, you have 90% of the question answered. And that's because what I call rule number 3 is the golden rule. Once you know which side is going to be favored, which way the reaction is going to shift, everything else is easy. And that's because my golden rule number 3 is whichever side the reaction shifts to, the concentrations always increase. Again, putting it in the seesaw perspective. If I'm going to push going to the forward reaction, the forward goes up, the back goes down. If I'm pushing backwards more, well, the back goes up, the forward goes down. So these things help me analyze questions. Now, the question that we're going to do is going to be a chart question. And you don't get a question like this on the state exam. You would get individualized questions on a reaction. But instead of typing in all the questions as they show up, I can put them in this chart-like manner to assess what's taking place. So notice here first, on top of my chart, I have N2 plus 3H2 gives me 2NH3 plus 91.8 kilojoules. They're all gases. I'm making a bond. And this time I'm using a specific amount of energy being released, which is 91.8 kilojoules. Okay. Notice my chart. I have what the question's going to be, what I'm going to stress. I have what I need to find out, what the shift is going to be. And then I have my reactants, and then I have my products. Because I want to know, if I do this to the reaction, which way will it go, and how does the concentrations of these things change? Now, you'll also notice in the chart, there are X's here. The X's, notice, are placed when the item is being used as the question. So for example, it says increase NH3. So that's why X is in NH3. We're not going to look at NH3. Here, we're looking at N2. So I'm not going to look at N2. Here, we're looking at H2. That's why the X is there. So as you see the X's, don't think we're solving for the X. The X is the stress that's occurring. So we're seeing what's happening to the rest of the reaction. Okay. So in this chart, what we're going to see is, we're going to see in the shift column, we're going to say right or left, forward and reverse. And then everything else is going to be an up arrow or a down arrow. Or if we see a catalyst later on, catalysts don't change things, so that remains the same. All right. So when we look at this reaction, the first thing you should notice is I'm making a bond, energy is being released, so it's exothermic. That's going to help me if this question involves anything with heat. Okay. And notice on this first part of the slide, I did not ask you a heat thing. It's all about concentrations. Okay. Second, once I know what the reaction is doing, I always want to focus on the shift. The shift is the most important thing. That's because in equilibrium, the seesaw application is, once I know which side it's going to, the golden rule, whichever side you go to increases. So that's why it's important. So let's take a look. And if you have to pause and go back and look at something again, there's no harm being done. You want to really understand what's taking place. So first, stress. I'm adding NH3. So the first thing I have to do is find out where NH3 is. NH3 is on the right-hand side. It's a product. Add shifts opposite. So I'm going to shift to the left side, which is the opposite side. Again, add opposite. I'm adding on the right. It shifts opposite to the left. And now I can apply my golden rule. I know it's going to the left, so everything on the left side has to go up, and whatever's on the right has to go down, and that's the energy. So notice, once you know what the shift is going to be, the golden rule is applied, and you can put these arrows in pretty quickly. Now, again, we're doing it in a chart-like manner. If you were asked a multiple choice question like this, it would have said, in the reaction below, when NH3 increases, what happens to H2? That's one question. Or it could say, when NH3 increases, what happens to the energy? Notice they're individualized questions on one part of the reaction. In a chart-like situation, we can assess the entire thing. Okay. And what we'll see is when we start doing multiple choice questions later on, I'm going to show you how I would attack the problem by up in this reaction, putting in what's happening, and then drawing bigger arrows to show which way it's going. All right. But for now, let's focus on what's happening and why it's happening. So take a look at number 2. It says decrease N2. So remember, the rule is remove shifts to the same side. So if I'm taking out N2, I have to find where N2 is. N2 is right here. It's on the left. So if I'm taking out N2 on the left, removing, it's going to go to the same side. So it's going to shift left. And as we said, once you know which way it's going to shift, the golden rule applies. Whichever direction you go in is going to go up. So that means H has to go up. It's on the same side. But NH3 and the energy have to go down. It's on the opposite side. Again, seesaw. Third example, H2 goes up. Add shifts opposite. It's on the left. I'm going to shift to the right. Seesaw goes up. Right side has to go up. Left side goes down. Notice it's not hard once you understand which way the reaction is going to go. And then what happens is after the reaction shifts, eventually it goes back to equilibrium until you stress it again. Fourth one, decrease NH3. NH3 is on the right. I'm decreasing it, removing it. Remove shifts to the same side. So I'm going to go to the right, which means the left side goes down and the right side goes up. Again, not too hard to do. The last one on this page says decrease H2. Well, remove shifts to the same. H2 is on the left, so I'm going to shift to the left, and therefore the left side must go up and the right side must go down. Now, again, you may want to watch this over 1 or 2 more times till it sinks in. If you got it, though, just keep moving on. They're all similar in the way that it works. Once I know the shift, I know how to apply everything else. All right, so let's take a look at the other side of the chart. So notice now I have 4 new things to assess. Increasing N2, pressure, catalyst. Same exact reaction, same exact setup. So it's exothermic, we knew, and I'm looking for the shift first. And notice there's only one X in this chart because the X refers to what the question's asking about in the reaction. There is no pressure in this reaction, okay? So we're assessing the whole thing. That's why it's open. So if I add N2, as you're thinking, that's correct. Add shifts opposite. N2 is on the left, so it's going to shift to the right. And therefore, the left side goes down, but the right side goes up. Pretty easy. All right? Now, when it comes to pressure, remember, pressure only affects gases. They're all gases. Pressure affects the number of moles or the coefficient. So now I need to add up the sides. So I have 1 and 3 is 4. I have 2 on this side. If I increase the pressure, I go to the smaller side. This side is 4. This side is 2. I'm going to the smaller side, right? So that's going to shift to the right. And if I shift to the right, well, right side goes up, left side goes down. So we should see down, down, up, up. Again, why does that happen? Increasing the pressure. Remember, box gets smaller, smaller side wins. Smaller side is the 2 side, which is the right side. That side goes up. If I decrease pressure, I'm going to get to the bigger side. Well, the bigger side is the 4, so I'm shifting left, and therefore the left side has to go up and the right side goes down. Again, not hard to do if you understand the concept of why this actually happens. Now, adding a catalyst. Remember, a catalyst speeds up a reaction by lowering the activation energy, providing a new pathway. It's going to speed up both directions at the same time. If it does that, there's no effect on anything else. So the catalyst has no effect. Everything remains the same. And whenever they ask you the catalyst question, it's always funny because there's three choices. It'll say increase, decrease, and remains the same. A catalyst only speeds up both directions, which has no net effect. All right, you know what time it is. It's your time to take a look at the worksheet. And once you look at the worksheet, again, feel free to come back to this slideshow.